guys, so we're looking at percentage purity. Sorry about the cat. We're looking at percentage purity today. So this comes into play usually because when we have chemical reactions, most of the time the reactants are actually going to come from an impure source. You're not going to have perfectly pure reactants taking or involved in your chemical reaction. Now with this sort of section of work, there are two formulae. One of them is a formula you have to just sort of learn. The second one is more of just a logic step that we can turn into a formula. And the first one, the one that you have to learn, sometimes it's on your formula sheet, but often it isn't, so rather just learn it. Percentage purity is equal to the mass of the pure compound over the mass of the source. Okay, so the mass of the source or of the sample, it's usually referred to as a sample, and because it's percentage, we times that by 100. Now what those words actually mean is, let's say we have a source of some compound, okay, and inside this source we're actually going to have pure compound, right? So let's say it's a source of magnesium oxide. Some of that is going to be magnesium oxide. So this red stuff I've put in here, that is our pure compound. But a lot of your sample, a lot of the source of your magnesium oxide or whatever your pure compound is going to be impurities. So other things that are not magnesium oxide. Okay, so we've got our pure compound and then we also have impurities. Okay, and in total, this whole thing together is our sample or sometimes source. Okay, so basically what that means is that the mass of your sample is equal to the mass of your pure compound plus the mass of the impurities. So this is our second equation, which is the more sort of just logical step. Okay, now in terms of what happens with these things, if this is involved in a chemical reaction, our pure compound is generally going to react and become something else. Okay, and your impurities generally are going to remain behind. Okay, now there are generally sort of two scenarios you can get. Either you can have a situation where we're just talking about the source and you have enough information just about the source to work out the percentage purity of it, or you'll get a situation where you've got a chemical reaction taking place, and from that reaction you have to work backwards to work out the percentage purity. So I'm going to do an example of each. So I'm actually going to pause you there. There's enough space to do the first example here, and then I'll erase for the second example. Okay guys, sorry, my black Coke is slowly starting to run out, so I'm hoping you can read that. We've got an impure sample of magnesium oxide, found to have a mass of 63 grams. When it is separated, 48 grams of impurities remain, and we need to determine the percentage purity of the sample. Okay, so in order to do this, we know we're going to be using the formula. Percentage purity is equal to mass of pure compound over mass of sample, okay, and then times that by 100. Now let's see what we have and what we don't have. We've got an impure sample which has a mass of 63 grams. So we have the mass of the sample. It says when it is separated, 48 grams of impurities remain. So this 48 grams is not the mass of the pure compound, it's the mass of everything else. Okay, so this 48 grams, that's everything except the MgO. Okay, which means if we want the mass of magnesium oxide, we're going to have to use this logic step here, the fact that the mass of the sample is equal to the mass of your compound and the mass of your impurities together. So if we have the mass of the sample and we have the mass of the impurities, we can find the mass of our compound. It's going to be the mass of our sample, which is 63, minus the mass of our impurities, which is 48, which means the mass of our pure compound is, let me see, 15 grams. Okay, so now we have this as well, and we can substitute in and solve. So we're going to get here 15 15 over 63 times 100, which gives us 23.81%. I'm hoping you guys can see that this low down on the board. Okay, so the percentage purity of this sample was 23.81%. So nice and easy if it's this type of example. So we had no chemical reaction. All of the information about the source or about the sample was given to us that we needed. Very unlikely you're going to get something like this in grade 11, and practically impossible you'll get something like this next year when you're in the trick. So don't bet on it. I'd rather show you the thing that you're more likely to see. Okay, so hang on for example 2. I'm going to pause you, erase, and we're going to do example 2. Okay guys, here's example 2. We've got a acid-base reaction taking place there. So we've got sulfuric acid reacting with potassium hydroxide to form water, and our salt here, which is potassium sulfate. They tell us that we've got 4.5 grams of an impure source of potassium hydroxide. So that doesn't mean we've got 4.5 grams of potassium hydroxide. It means our potassium hydroxide comes from an impure source, and the mass of that impure source is 4.5. Okay, and it says it's reacted with excess sulfuric acid to produce 5 grams of potassium sulfate. So reminder, excess sulfuric acid just means we've got more than we need, we've got enough, and we're producing 5 grams of that salt, K2SO4. Okay, so we've got 5 grams of this being produced. This 4.5 grams, I'm actually going to make a note for myself immediately up in the corner here. I know the mass of my sample. Okay, the mass of my impure sample is 4.5 grams. That's the denominator in our percentage purity calculation. Okay, that's going to be that. Okay, question A says to balance the reaction equation. So I'm just going to go ahead and rewrite it, leaving space for balancing numbers. Okay, and let's balance it. So I've got 2 potassiums here, I need 2 there. Sulfate, that's fine. 2 hydrogens, that's fine. But actually it's not fine because I've got 4 hydrogens on the left. Those 2 and now those 2, which means I need a 2 here. Now let's check if my oxygens are fine. I've got 2 6 oxygens, I've got 2 6 oxygens. Okay, so this is it balanced. A 2 by the potassium hydroxide, a 2 by the water. Then question B, determine the percentage purity of the potassium hydroxide source. Now for percentage purity we use the formula that says the mass of the pure compound divided by the mass of our sample times 100. Now we've got the mass of our sample. We do not know the mass of the pure compound. This 5 grams is the mass of potassium sulfate, not the mass of potassium hydroxide. But we can work backwards. If we know how much potassium sulfate was produced, we can determine how much potassium hydroxide reacted. And that potassium hydroxide that reacted, that would have been the pure compound within our impure sample. Okay, so we need to figure out the mass of pure sample. Okay, and we're going to do that by doing reaction stoichiometry. Okay, i.e. the amount of potassium hydroxide that reacts is what we are looking for. Okay, so in order to do that, it's going to be what we've been doing for the last couple of days, those last 2 worksheets you did for me. We know how much of this is produced, we want to know how much of this reacted. Okay, so same process we've been doing. So starting off with the number of moles of K2SO4 equals the mass of K2SO4 divided by the molar mass of K2SO4. I'm worried about running out of vertical space, so I'm going to go sideways a little bit. So that is 5 grams. Molar mass of K2SO4 is going to be 2 times 39. Again, I'm using a different periodic table to you guys, so my molar masses might be like 1 different to yours, so I'm sorry about that. Plus the molar mass of sulfur, which is 32, plus 4 times the molar mass of oxygen, which is 16. Okay, and we get that the number of moles of K2SO4 is 5 divided by 5 we get 0, now remember you try and keep a number of decimal places here when you're in the middle of your calculation. So 0,02874. I'm going to call that enough decimals for now. Okay, next up, so we've got the number of moles of what we knew. Now we need to take the moles of what we know and convert that to moles of what we want using our balancing number. So remember there's a 1 there and a 1 there. Okay, so we go in K2SO4 to KOH. This is 0,02874 to the number of moles of KOH is 1:2. Okay, so remember we're going to take this number, divide it by 1, and then multiply it by 2, and that will give us the number of moles of KOH. So that means the number of moles of KOH is equal to the number of moles of K2SO4 divided by 1 times 2, which is 0,02874 divided by 1 times 2, which is 0,0575 moles. Okay. Now we know the moles of potassium hydroxide. Let's check. That's not what we want. We want the mass of potassium hydroxide. So we're going to do this formula again, but now we do it for potassium hydroxide. So number of moles of KOH is equal to mass of KOH divided by molar mass of KOH, which is, okay, so we know moles is 0,0575, equals mass of KOH is what we're after. Molar mass of KOH is going to be 39 plus 16 plus 1. So then we get the mass of KOH is 0.0575 multiplied by 56, yeah. So the mass of KOH here is 3,22 grams. Okay, now we're not actually finished. We've worked out the pure, what mass of pure potassium hydroxide we have, but that's not what was asked. We were asked to determine the percentage purity of potassium hydroxide. So now we can take this number and put it into this formula. Okay, we can now say percentage purity is equal to 3,22 divided by the mass of my sample, which is 4,5 times 100. So divided by 4,5. So we get 71.52%. Okay, so this sample was 71.52% pure. So I'll quickly see how much space we've got at the bottom to do another question. Okay, none at all. Okay, so we're actually gonna, can I just move this down a bit and then we might have a bit more space. Yeah, okay. So I'm gonna try write small, sorry about that. So let's just do one more question. It's a quick one, as you can see by the space. We're going to determine the mass of the impurities. Okay, so for this, it's just that little logic step where we know, well, the mass of the impurities and the mass of my pure compound together must give me the mass of my impure sample. So for this, we simply have to say that the mass of the impurities is going to equal the mass of our sample minus the mass of our pure compound, or just the mass of potassium hydroxide, which is going to be, our pure sample was 4.5 grams, sorry, our sample was 4.5 grams, our pure compound was 3,22 grams, and we get 4.5 minus 3,22, that's 1,28 grams of our potassium hydroxide sample was impurities. Okay. This is sort of normally the last question of the stoichiometry section. It'll usually either be this or percentage yield, which is still coming. Yeah, they can also actually ask it slightly differently that's worth noting. So if we look at this formula here, just put a blocky around it. So if we look at our main percentage purity formula, they could sometimes talk about a reaction and they give you the percentage purity and they give you the mass of the sample, and then you would just have to put them into this equation and you could work out then the mass of your pure compound from that. Okay, so they might sometimes ask you to do it backwards, but as long as you've got this formula and you know how to solve an equation, which you learned how to do in grade 8, you should be fine with this. Okay, I am going to also WhatsApp you the worksheet. I'm sorry, there's been quite a few little silly errors on the worksheets lately. My brain is also sort of all over the place with this quarantine thing. But please do continue to question me if you think there's something weird going on a worksheet or on a memo. And also obviously ask questions if you're getting stuck. I'm glad to say that your class has actually been the most vocal during the quarantine. I'm actually very proud of you guys. So well done. Keep it up.